Welcome back to the DemystifySci podcast. I'm Anastasia.
I'm Shiloh.
And this is the place where we search for the theories and ideas that are going to change the world. And today we have a conversation that is one of the most intense and emotional and outrageous conversations that we have ever recorded on this podcast. It seems extraordinary that such a conversation could be recorded on a subject as dry as the cosmic microwave background that is believed to come from the birth of the universe. What we are proposing in this conversation is that the fundamental physical interpretations of the cosmic microwave background signal make it impossible for it to come from the Big Bang. Our guest for the conversation is a world-renowned cosmologist at UCSD, Brian Keating, who invited us very generously to his office, where we sat down and we asked him, if this is how these signals work on Earth, in the laboratory, every single time that we have ever tried to create them, how is it possible that this signal is coming from the Big Bang? And this is where the conversations start to fall apart, because if the cosmic microwave background signal cannot come from the Big Bang, then cosmology is in a lot of trouble.
Brian probably has a different interpretation of why his reaction is so strong to the ideas that we put down right at the beginning of this conversation. But I want to take a moment to explain why I think that it's such an emotionally charged topic for a cosmologist to engage in. And it comes down, like you said, Nastia, to the particular fingerprint of the light that comes from this microwave background signal. That particular signal is something called a blackbody spectrum, which sounds a little weird and technical, but the reality is that when you heat up a solid or liquid body here on Earth and you split the light that comes from that glowing substance with a prism, you see a very specific continuous rainbow of color. Now, the problem with attributing such a rainbow of color, like the one in the microwave background, to the beginning of the fiery universe is that it's being attributed to a gaseous moment in the universe where the first atoms were just recombining and straining out this light that just happened to be flying around. The problem with that is that whenever we take such gaseous atoms and heat them in laboratories, we don't see a continuous, beautiful rainbow. We see individual lines. Gases produce individual frequencies of light. Sometimes they produce many different frequencies, but they're always discrete spikes in a spectrum. Now, what gets very bizarre about this is that the idealized form of a heated body is only possible with a very particular body. That particular body is all black. It's a perfect absorber. In other words, it can take all light and turn it into heat, and it can take all heat and turn it into light. And it gives this very particular fingerprint called a blackbody spectrum, which you can check out here. We have no reason to believe, based on any laboratory analysis, that a gaseous plasma, anything other than a heated solid or liquid, can produce such a spectrum. Now, astrophysicists for the last 100 years have acknowledged that this tends to be the case in laboratories. You can't do it. But they always point to the stars as if, well, the stars have this beautiful continuous blackbody spectrum, or at least something very close to a perfect blackbody spectrum. It's not quite perfect, but very, very close. If the stars can do it, and the stars are gaseous plasma, well, then why can't the beginning of the universe's gaseous plasma do the same thing? Well, that's where we end the conversation, because there's good reason to believe that the stars aren't a simple ball of gas that we've been taught. That conversation's for another day, and hopefully we'll be having Brian back to discuss that possibility in the future. Whenever Nasi and I are out and about and talking to people about these ideas, one of the first things they always seem to, if not say, they seem to be thinking is, why in the heck am I hearing this from you instead of some Nobel Prize winner? That's a really good question. And there is some precedent for answering that question. One of the central stories of cosmology, if you take an intro astronomy course, an intro astrophysics course, you will almost certainly be confronted with the first cosmological revolution. So for the first couple millennia, most of the first couple millennia, there was a popular cosmology. There were some astronomers who had made incredible star maps. Their conclusion was that all of these bodies, including the planets, moved around the Earth, not around the sun as we understand it today. This is all to say that having an extraordinary mathematics to back up your cosmology is not sufficient to make it correct. And that's where things start to get very bizarre with the modern paradigm.
I think it's worth realizing, too, how radical of a reimagination Copernicus demanded of every single person on Earth when they went and looked at the cosmos and realized that the way that they thought that they saw the motion of the celestial bodies was not the right vantage point to have. Like, you had to stand at the center of the solar system. You had to stand on the sun in order to be able to see the much simpler, much clearer picture of what was actually happening. And if we say that the cosmic microwave background has to come from a heated liquid or solid, I don't know how much that changes the story of the Big Bang. Something that came out over the course of our conversation with Brian is that there are so many pieces of evidence that fully integrate into the theory of the Big Bang that it's going to take years, if not decades, if not a century or more, to fully untangle what this means for the story that we tell about the cosmos. But what I do know for certain is that we have to talk about it. There appears to be something very, very strange about the cosmic microwave background, about the kind of signal that it is, about the kind of physical reality that is required to generate it. And if we do not pay attention to that, if we do not think about it, if we do not talk about it, if we do not share our ideas on where that might come from, then we are doing a disservice not just to ourselves, not just to the art and practice of science, but I think to the entire human species. Because what we do, as humans, ideally, is we search for better stories to tell about how nature works. And the story of the cosmos, the story of the Big Bang, the story of how all of this got here, and the story of what is going to happen to it in the future runs in the background of all of our lives constantly.
And if we're not willing to take a close look at that giant meta story at the heart of science, really, then we are really risking our approach to science in general, which is extremely important because if you look at the way that people interpreted the world prior to science, it was really a kind of anything goes situation. And that's what we're scared of.
And so before we get to the conversation, I just want to express a deep and abiding gratitude to Brian because he did not have to invite us to his office. He did not have to sit with us for this entire conversation. Despite the fact of how difficult it was, he chose to remain and he engaged with us. And I could tell that he wrestled deeply with the ideas. And that is what we need more of. And so I cannot say thank you enough to Dr. Keating for having us, for hosting us, and for letting us have this conversation.
One more thing we need to mention before we get to the conversation is that this podcast is entirely paid for by you guys, the listeners. So we work directly for you. But we just can't do this without your support. And a couple of ways, I suppose, that you can support the project. Firstly, come over to Patreon. See if that is a community that you could contribute to. We get together once a week with our patrons. I love seeing you guys. If you're already a patron, thank you so much for making this happen. Honestly, it's incredible to be supported by such a deep thinking and careful group of minds. It's really incredible. You can also support the podcast by picking up some gear. We design our own gear. We got some different designs down on the YouTube shelf. And we also have some music. We finished our first album and we've been selling vinyl copies of that record, which you can pick up at a link in the description. All of this goes towards making sure that we can put more and more of our time towards this project.
There's one other last way that you can support us, which is actually brand new. Shiloh and I have almost finished our first book. It is called Paradox Lost: The Material Principles of Natural Philosophy, and it is a breakneck exploration of the history of physics and the future of physics. We asked the question of how it is that physics lost touch with the material mediators probably almost 10 years ago. And this book is the sum total of all of our research into it and a theory about where science can go next, about how we can take these strange disembodied forces and fields and actually put a shape to them. And so that's going on pre-sale. It's going to be finished in a few soon. It's going to be finished in a few soon. Shiloh gave me a look to say, be careful what you promise. But if you want to pick up a copy of that, a pre-order, then the link is here. And we really hope that you will support us in our quest to finally make sense of the greatest mysteries of physics.
So enjoy the conversation today and check out some of our music as we lead into the conversation. We'll see you next time.
So come out, you put us to the test. There's no prize neath your skies that would see us settling for less. We won't be settling for less.
I think that we should start where we left off last time. So we came 2 years ago and had a relatively abridged conversation that started very broadly. We talked about, what does it mean to quote unquote believe in science? And we ended on this very tantalizing question of, okay, well, we agree that science is not something that depends upon our belief, and we recognize that theories change, and yet everybody seems deeply unsatisfied with all attempts to change the central theory of astrophysics and cosmology, which is the Big Bang. And we've spent the last 2 years really exploring the ideas that are attempting to replace the Big Bang. We had this big conference in Portugal. We invited a bunch of people. It was about the future of cosmology. And over the course of these 2 years, we've come to the realization that there's 3 main pillars that seem to be supporting the Big Bang. And this is elemental abundance in the cosmos. This is the apparent reddening of all light across vast distances. And it is the cosmic microwave background radiation. And given that you have so much experience working with the CMB, this strange, cold signal that comes at us from all corners, I wondered if we couldn't focus the conversation today for the hour and a half, for the hour plus that we have, on the CMB and talk about what would it look like to really dig into it and to ask a very difficult question, which is it possible that it is a signal that is real and measured, but that the story that we're telling about it is not the best story? And to get there, I wonder if you couldn't bring people along for the conversation by starting with a brief explanation or description of what the CMB is and why it's so important for cosmology.
Sure. But first I have to, raise an objection to the fact that my invitation to Portugal must have gotten lost in the mail. In the email. I checked my spam folder multiple times. I even run a monthly, office hours with some high-level contributors to my YouTube channel. And one of them was there. He goes by Memes of Destruction. So,
Yeah, shout out to Matt.
Yeah. So, anyway, congratulations on doing that.
We're doing another one,
Oh,
and
wow.
you will absolutely get an
Okay.
invitation, my friend.
This time I'll check the spam folder every day. So it's not at all a surprise that the CMB, or cosmic microwave background, is so centrally important, both to the, kind of qualitative description of the Big Bang, which, I think is a story most people are familiar with, and we can get into more details about it if you like, but I assume from watching and being a part of your wonderful show that a lot of the audience will be familiar with. So I want to go a little bit higher level. So humans by nature are visual creatures. If you look at what's called the motor homunculus, which is a depiction of the weights given to different aspects of the human physiology. So there's a depiction. It's a very strange looking creature. Maybe you can put it in B-roll, but it really shows you what evolution or God or whatever you like has paid attention to. And there's 2 major attributes of it, and the rest are like almost afterthoughts. Like the pinky toe is really not something we think much about unless you drop something on it, as I often do. There's 2 things. There's the hands manipulators of the interactions with the physical world, and there are the eyes. And those are the two most important aspects of the human body that the brain or evolution has really spent a lot of time optimizing for. And so if you take away the mechanical interactions via the hands, which is what I do as an experimental cosmologist, I don't come up with theories. I understand theories very well. I work on aspects of testability and phenomenology associated with it. I don't make new theories, nor is it part of my job description. But I build instruments, and my colleagues and I build instruments, and they're the pinnacle of the construction of this field. There's no experiment that really will top for maybe a long time, maybe ever, the Simons Observatory, which is a project that I co-lead in Chile. So that's dedicated to the optical part, the part that you're trying to glean information about the outside world from its appearance, from the way that it presents itself to you. And as Galileo said, 400 years ago, a scientist must do the following: he or she must measure what is measurable and make measurable what is not yet so. So he was basically talking about instrument building. You'd have to construct sensors that translate the paucity of physical signals that we get from the observable universe into something the human mind can then grapple with, iterate on, construct different improvements upon, and so forth. That's what the scientific method is, despite what you were taught in 9th grade biology, right? So from the perspective of the cosmic microwave background, it is the oldest light in the universe. It's not the oldest radiation in the universe. It's the oldest light in the universe. And as such, it has this outsized importance in the uncovering of the physical reality that we are privy to. We can't see things that are unobservable. We can try to make them if they're potentially observable. For example, neutrinos are very long-range carriers of information, cosmological possible information, almost impossible to think about detecting the cosmic neutrino background, other than its interaction with the cosmic microwave background itself. So the CMB...
Why do you say it's the oldest, by the way? Is
the light, the CMB?
Mm-hmm.
So
that apparent, or that's mapped onto the theory that's being made about this, or
so they're just as they're the oldest light in the sense that when you came here maybe a day or two ago, there was a thick cloud layer called the marine layer here in San Diego, which normally comes in May, and we call it May gray, or June, we call it June gloom. And it's a layer of light that represents the last scattering of photons before they reached your eye. Okay, so it's a cloud layer, an overcast layer. You can see everything from here to there, but you can't see anything above it, beyond it, with optical light. But you could hear things from beyond it. So there is radiation. Sound waves are a form of radiation. They travel like a plane flying above the overcast. You can hear it, you can't see it. The reason you can't see it is because the light is so thoroughly scattered by the water droplets in the cloud layer that's why it appears white. It jumbles up all wavelengths, makes them combine together. And it also prevents, it has a very extreme optical depth. You cannot see through the cloud layer using your eyes. You can see through it with other wavelengths, right? Radio waves go right through it, microwaves go right through it. So too, the lesson is...
They can have a hard time though, too.
Yeah, don't they get blocked by the clouds and the water?
Maybe not blocked, but they
blocked.
They get us in trouble.
Well, so you have to distinguish between what you might consider visibility or blockage, right? So there's wavelengths that are completely obscured by the Earth's atmosphere, but not by clouds. There are wavelengths that are obscured completely by clouds, but not by the atmosphere. And then there are waves that get absorbed by both of them, right? So there's a tremendous amount. For example, ultraviolet light is a very hard time getting through the atmosphere, the ozone layer, right? It also can't get through clouds, so that's sort of an extra impediment. But getting back to the CMB,
dating the light, yeah.
Yeah. So the CMB results from an earlier time in the universe's history when it was hot enough such that there were no molecular or atomic hydrogen atoms. Okay, there was no ability for them to be existing because the universe's temperature was far higher than it is today. So the temperature scales with the redshift, linearly with redshift. And so when the universe underwent an earlier phase, you don't have to posit the Big Bang. You do have to posit the universe was hotter and denser, and that there's hydrogen in the universe. But all of these are observable. All of these can be detectable by instrumentations that we build and other teams have built going back to 1965. So we have known about this light, and it was the result of the scattering of light that existed before the CMB was produced. And it existed up until the time the first hydrogen atoms formed. Okay, so behind you is a bottle of water, which used to be ice from the South Pole. See that little Nalgene container there? That was scraped up at the South Pole. And it has melted over the last 20 years since I've collected it, but there it is, right? It's got a lot of hydrogen in it, right? So, but originally it was in the form of snow and ice. You couldn't see through it. But once the hydrogen, once the oxygen, once the water is formed, it becomes transparent. You can see through it. It doesn't trap bubbles. And so it has these properties that we understand extremely well. Hydrogen is the most abundant atom in the entire universe by mass, by number. It's an incredibly important element. We know its properties exquisitely well. We can measure them here. We can measure them in other galaxies. We can measure them on other planets. Their properties don't change. There's no evidence that there's any large-scale changes in the evolution of these atoms or of the properties of the atom or of the speed of light or of the nuclear force, of the weak force. There are no evidence whatsoever that it's changed over billions of years, let alone since the CMB is formed, right? So once you stipulate that the universe has hydrogen and the universe was smaller in the past than it is today, that the universe is expanding and there's infinite amounts of evidence.
This is from the redshift data.
Well, there's more than just redshift. I mean, you can measure redshift locally from a variety of different sources. You can measure intrinsically what cosmologists do. We would like to measure the distances between different objects. We don't have rulers that stretch billions of light years away, right? So we can't physically measure something. So we make proxies for these measurements in terms of things that we do understand well. And we make what's called a calibration ladder, a rung after rung that takes us from distances on Earth to distances in our solar system, to distances in our galaxy, to distances in the nearest galaxies, to the distances within clusters of galaxies, to superclusters, megaclusters, and then to the farthest distances we can see, which are traced by baryon acoustic oscillations, which we can talk about. There's been a lot of recent discoveries with that recently in the past year or two since we met last, and going back all the way to the CMB. As soon as you go back to the CMB, the universe is too hot to have actual atomic hydrogen. So it has the nucleus of hydrogen, which you just call a proton, or in the case of deuterium, which is also present in that water, which is very crucial, that came from the combination of a proton and a neutron, right? That's what deuterium is. There's a tiny bit of tritium, which is 2 neutrons, 1 proton.
Would it be deuterons at that point if it's a charged version of it, or no?
So deuterons have the same charge as hydrogen, as protons. They're just 1 proton plus 1 neutron. That doesn't change anything, but it's an isotope. So it has slightly different chemical properties, slightly different atomic mass, but it's a minuscule amount because the neutron, it's the effect of the neutron added to the proton doesn't change a lot of the chemistry whatsoever. It changes the density, it changes some other physical attributes of it, but it's not, you can make ice out of it. It's funny, the ice will sink in water, unlike ice cubes of ordinary water, protium water, that will float on water because they're less dense than the water that surrounds them.
But it seems like you're saying that you assume the CMB is an old light source because it maps onto the giant narrative that it is the result of this event that happened deep in the past.
It's not just a narrative. I mean, you can kind of stipulate everything.
Well, evolution's a narrative. I mean,
calling it a narrative is slightly, denigrating what it is. Really, it's not like a folktale or a campfire song. I mean, it's the most precisely tested element of physical cosmology. Absolutely. That redshift occurs. It's tested in every single cosmological instance.
It's an empirical fact, right? That there is this redshift apparent. It's an empirical fact that the CMB isn't. You can measure it on Earth. You can measure it in satellites above the Earth. You can measure it in weather balloons. These things are all apparent. I didn't mean to denigrate the theory. I'm just saying that we have to stitch a story together as scientists about what this really robust data means at the end of the day.
Sure, but that's an attribute of science, not of cosmology uniquely, right? You have to have some interpretation. When I say F equals ma, is that a narrative?
Yeah.
It's this description of what is apparent. I think that the curve fit for the Hubble relationship is a description of what's apparent, but at least in other sciences, perhaps besides physics, like the theory is the statements of the the Big Bang. It would be the story of what causes these curves to look the way that they do. It was pinning this ever-present source or this really robust piece of data to really a story of where it came from in the past. And
I agree 100%, but I would say that F equals ma is also a narrative. It's also a description. It's an empirical observation. It's not provable in the way that the piano axioms allow you to prove that 1 + 1 = 2, despite your friend Terrence Howard and my friend Terrence Howard objection that one times 1 equals 2.
He did find a breakdown of calculators, which was quite interesting.
He did, yeah. He's a very creative individual. Let me just say that. I have yet to meet him, but let me just say. So in the observational and physical sciences, there's no such thing as proof, right? So and even within the context of mathematics, you could also say the piano axioms, you could say that Gödel's theorem, those are narratives and stories, but you have to be careful. And there are narratives and there are other narratives, right? We could say the Earth looks flat. That was a narrative that was actually very sustainable. I mean, if you ask 90% of college freshmen on this campus, can you prove the Earth is round? Or is the Earth round? They'll say yes. 100% of them will say yes. And if you ask, well, prove it to me, I would say probably 10% could do that.
Interesting.
And they're top university in the world. I mean,
it's a very clever little move. That who was the Greek guy? You probably know his name.
It was Aristarchus.
Yeah, I was getting messed up with Aristophanes.
Yes, You're not alone. And then if you want to go really old school, get medieval on them. Literally, you'll say, well, okay, I believe that the sun orbits the Earth. Prove me wrong. I would say 99% of people can't prove that. Even extremely educated people. I like to do
phases of the moon, guys, or phases of Jupiter's moons.
That doesn't actually prove it.
Phases of Venus.
The phases of Venus doesn't prove it either.
Oh, come on.
That could be Venus. So to be devil's advocate, no, the first proof of it was called stellar aberration. So it's the discovery that because of the great distances to stars,
that was much later.
It was much later, yeah. So Galileo tried to prove that the Earth went around the sun by using the Earth's tides as his dominant piece of evidence in the Dialogo, which I turned into an audiobook with Carlo Rovelli and Lucio Piccirillo and other people for the first time ever. We have an audiobook by Galileo, but he claimed that was actually in the title of the dialogue. It was, the dialogue on the two chief world systems by virtue of observations of the behavior of ferns, which I don't even know what a fern is, but apparently it's like the inverse of a fjord, and rivers and oceans. Anyway, he claimed that the sloshing motion as the Earth went around of the tides, as the Earth revolved around the sun and rotated on its axis, that's what caused the sloshing, caused the tides. Of course, that has nothing to do with it. The moon causes the Earth's tide. But he was right for the wrong reason. His narrative was correct, but it was completely unsubstantiated by scientific truth.
Okay, so I think that we run the risk of getting a little bit too meta. And the meta conversation.
Can I add one tiny thing I really wanted to add? This is the perfect situation because those guys had an incredibly the Ptolemaic astronomers, who were basically the academics at the time, they had a really powerful model that was super predictive and super accurate, just like you guys do. It was completely badass by all assessments of the day.
Yeah.
But it turned out to, just need a different perspective a little bit, right?
The crazy thing about the Ptolemaic model is that it is not inaccurate in terms of describing how things look from the vantage point of Earth.
Sure, and so is the flat Earth.
And that's the crazy
Flat Earth also appears great. I mean, you probably got here not computing spherical trigonometry. You use Google Maps, which is a flat Earth approximation that's local to our tangent point on the Earth's globe surface. So yes, you're right. There are context-dependent things, right? But to get back to the original point. We understand plasma physics exquisitely well. We understand quantum mechanics exquisitely well. And so we know the properties of height. Look at the periodic table over there. We understand all the elements. We understand their binding energies. We understand how they form. Are there things we don't understand about? Of course, there's always going to be things you don't understand. And that's what makes being a real scientist really a lot of fun. However, if you look at the body of evidence, the compounding of evidence that we have, that the CMB results from a denser phase in the universe's history. You don't have to postulate it's a redshift. You don't have to say anything about redshift. You can just say, if the universe was hotter and denser in the past, hydrogen could not be a stable atom. That statement has nothing to do with cosmology. I mean, that doesn't have anything to do with the birth of the universe, right? I mean, what I know you guys are trying to make a very interesting distinction that the Big Bang is a model, and there could be other models, and we could talk about those other models.
I don't think that, no. So we're trying to, the place where we're trying to go is we're trying to say that, look, it seems like there is a really well-characterized body of knowledge about black bodies, about black body radiation, about thermalized radiation, and there
The
appears...
CMB, we didn't even mention that it is a
Sorry, I
black.
keep switching the camera. I'm used to the fact that when you talk, I switch the camera to you, but I keep... Sorry.
Well, we didn't even mention that the CMB is a black body source.
Yeah.
Sorry.
So it's like the CMB is the universe's best black body signal. And so black bodies are kind of this crazy unsung hero of physics, because if people in physics know about black bodies and they really care about them, you tell somebody on the street about a black body and I think that they're going to be like, what? Like, they see the fact that there's Kelvin ratings on their light bulbs, but it doesn't connect to some kind of deeper physical principle. Yeah. And so it's also at the basis of quantum mechanics, so it's this massively important theory.
Well, it's also the link between classical mechanics and quantum mechanics, I would say.
Yes.
It really was a classical discovery that motivated the quantum corrections that Planck made, right?
Exactly.
So you're right. It has this outsized importance, but in cosmology, we observe it as a black body, as you said. It's the most perfect black body we've ever encountered, which means that we can calibrate instruments according to the CMB itself. Right, which means that it doesn't suffer from deviations from there are quantifiable deviations from a perfect black body, which have a lot of the Planck formula, or have a lot of the Bose-Einstein properties. So I should take a step back. Black body or Planck radiation spectrum is a special case of the Bose-Einstein distribution. So Bose-Einstein describes the properties of bosons at a given temperature in a given what's called a chemical environment, a chemical potential, and interacting with a medium. It has the certain properties that it doesn't have a chemical potential. It's only dependent on one number. One number characterizes every black body that has the same temperature, has exactly the same radiation photon density. And that's the Planck distribution. That's the Planck limit of the Bose-Einstein distribution. So to say that it's a black body kind of undersells it. It's the most perfect black body, meaning it could have three different types of deviations: Compton Y, chemical potential, other higher order functions. It could be not appear at all the way it does, but it does. And in fact, we can use it to calibrate all sorts of things, including these lights, right? You trace it to that perfect calibration.
And that's what's crazy.
Yeah.
And that's what's crazy, because on Earth, in terms of the black bodies that we are familiar with and that we use...
Like laboratory ones, eh?
Laboratory ones... Are there other ones?
I mean... Yeah,
I'm
just talking about you said
that are in use in the world, because I think that it's not... I mean, I don't think it's just laboratories. The incandescent light bulbs also use the same principles. But the point that I'm trying to make is that there are fundamental physical principles that govern what allows an object to be a black body and to approach perfection, right? So like the main principle of black bodies is that the spectrum of the radiation that they release, it has this particular shape, very abrogated in the high frequencies. It has some peak level of radiation intensity, and then this kind of long tail into the longer wavelengths. That shape, if you take the peak of the distribution, the thing that Planck did is he famously came up with the equation that actually accurately predicted that. There's a physical requirement for objects to appear perfect. And it's
in the laboratory.
In the laboratory. And so that's the piece that we're really trying to understand, because all experimental evidence that we have on Earth suggests that black bodies require specific lattices. Like if you take carbon, a carbon atom placed in a Bunsen burner produces individual line spectra. It can absorb and emit at certain individual wavelengths. Okay, great. You take that carbon and you put it into a diamond lattice, totally see-through to visible light, absorbs really, really well, I think in UV and infrared. Like if you hit it with infrared and UV, it gets really hot. And so it's black to those frequencies. And then if you change the lattice of the diamond to be graphite, As you increase the perfection of the hexagonal lattice of the carbon arrangement, you get closer and closer and closer to something whose radiation profile looks exactly like this predicted perfect Planckian distribution.
And it's a perfect absorber.
And it's a perfect absorber because it can take in those wavelengths. And it's also really crazy because you can't have black bodies that go into the super high frequencies. You can't have gamma rays or even hard X-rays interacting with black bodies. And so it feels like there's something that is deeply material that underpins.
There is, but it has nothing to do with lattices. I mean, you can have a plasma that makes approximates that
You
very
can't. So
you certainly can.
the reason that we think that is because we point to the sun.
Not
Well,
just the sun. I mean,
yeah.
any in a tokamak, you can produce a black body.
They don't
spectrum.
produce black body radiation.
It depends on the temperature, the composition of the tokamak.
They
What is
don't.
tokamak made of? I mean, what do you think it's made of?
Do you mean the surface of the reactor?
No, not the surface. What is it doing?
What's confining plasma using magnetic fields?
Right. So that's one incarnation of it. Sure. Yes. So when you have that, what is it? What's in there? What is plasma? What do you think plasma is?
Just a super excited form of atomic matter. I mean, it's ionized, I
It's not
suppose.
ion. It's not atomic. Yeah.
There's
It
no
could be, it's
atoms?
pure electron. No, it's pure electrons.
Wait,
The electrons.
so you're telling me
There
there's
are
no-
protons obviously in there too.
Okay.
Right.
Well,
But
yeah,
it's not
that's
a lattice.
important.
Yeah.
Well, that's the thing is that okay, so that's really important because we literally have gone down the rabbit hole of this. There is no plasma on Earth that produces a perfect thermalized spectrum. It does not exist.
Like a Planckian
Of course, yeah.
line.
There's
line
nothing that
curve.
even the CMB is not perfect. I guess I fail to see what distinction you're making. I mean, first of all, the Planck body, the Planck radiation formula is important because it could only be derived from a thermodynamic standpoint once you accepted the quantization of photonic energy.
Sure.
So that was the key insight. And once you quantize photons, then you have some cavity. That cavity only admits certain wavelengths and then certain approximations. That's why there's a Wien tail, there's the Rayleigh-Jeans region of it. These are all things we observe, not in the CMB itself. We observe these in gas clouds in the Milky Way galaxy. So there's no sense that
is just one frequency, right? That you're
no,
picking.
it's a huge range of frequencies. Any part,
But you're
basically
picking
long.
one and you're grabbing the temperature from one frequency, right?
No, but you can get it from, it's a linear approximation to the low frequency slope of the black body radiation, which is independent of anything else besides the black body temperature.
But hold on, but the thing that we're trying to get to is we're trying to say that, like, look, there is this piece of this theory that says we have this light, and this light must be from the birth of the universe before there were atoms, because it is...
No, it's not coming from before there were atoms. It's coming from the formation, after the transition period between 100% ionized plasma, a pure plasma, and a neutral atomic distribution.
Yeah, I've always understood that it's the leftover...
You were saying like scatter. You're saying it was scattering this early glow.
So a plasma typically has at least two ingredients: ions or electrons and photons. To talk about when you talk about the temperature of a black body, what is it that you're talking about? What temperature are you talking about? The temperature of the photons, the temperature of the ions. What do you think is being characterized, right?
Well, I think
the nice thing about a perfect black body in a laboratory as a cavity is that when whatever is inside of it is at thermal equilibrium with it, it will transform all the radiation from that body into thermal energy, and so its temperature will be accurate and reflect the temperature of the rays.
If you are listening to this conversation and you are enjoying it and you are enjoying yourself and you are wondering, what can I do to make sure that more of these ideas get spread throughout the cosmos, then think no more and just come over to patreon.com/DemystifySci. We meet with our patrons once a week at Sunday salons, and you get to live with the sweet satisfaction of having supported something that you love, cherish, and want to see more of in the world for just 75 cents a week. See you at patreon.com/DemystifySci.
Thermal energy is a molecular concept. It's maybe an atomic concept. It's not a quantum concept, right? So I guess, where are you going with this, guys? I'm kind of missing the big picture, maybe. But
the big picture is...
Do you want to say... let me just cut to the shit. I think what you want to say is that everything you believe about the CMB is predicated on the fact that the universe is expanding. And because of that, you built in an assumption what you're trying to prove, that the Big Bang happened. But I can tell you there are aspects of the CMB that are present and can be evaluated instantaneously at the formation of the CMB. In other words, not looking at, well, how far away is the CMB surface of last scattering, which is a very important concept, which only bolsters the case the universe has been expanding, because you have acoustic oscillations that form on a given time scale that give you a standard ruler, which we use to measure the distance of the last scattering surface, which gives us the age and the expansion of the universe, the Hubble constant.
I don't think we have any problem with the Big Bang or anything like that in this conversation. I think it's more just, is it reasonable to expect such a black body source from anything other than condensed matter with a lattice? Because we've never been able to, like, the thing that look, you can't get a Planckian spectrum from a tokamak. You just can't. That's just not true.
You can certainly get an approximate temperature, as you talk about. We have to get to some temperature, right?
Can I just add one tiny little thing? Mm-hmm. Like, even with lattice-bound objects like carbonized substances.
You say lattice. Hold on a second. You guys keep saying lattice. Do you mean crystal?
Just condensed matter.
Okay, so you mean, but you could have a fluid that's not a lattice, correct?
You can get black bodies from fluids, but my point is that even when we go into the laboratory and try to create a perfect black cavity, we have variations in emissivity. Like, we won't be able to make it perfect, but the way that we get closer is by fine-tuning the lattice. We really change the structure. We don't change the molecules the elements that go into it.
That's a lack of our ability as experimentalists to construct something that's a perfect emitter and absorber. By definition,
but the way that we get closer is by tuning the lattice. Isn't that interesting?
But when again, you keep saying tuning the lattice.
We only have the crystal structure of the substance.
But again, you just admitted it's not crystal only, right? It could be a liquid, which is not a crystal.
But liquids have structure inside of them, and so basically, like, the thing is that even
liquid's definition is that it doesn't have structure. That it assumes a shape of the container. There are gases and so forth.
Like, people study water; it has a transient lattice structure. That's actually what I did my PhD in, was in the transient lattice structure of water. So it's like,
you can certainly form it into a crystal. Yeah, that's true. But
no. Like, liquid water has lattices that are transient in the liquid matrix.
This is the water molecules will swap out, but the structure still remains. It's quite perplexing. It's a really beautiful phenomenon.
Yeah, that sounds interesting. It doesn't sound necessarily relevant to what we're talking about. But
no, what's really cool is that to get really... So look, the CMB is the most perfect black body we've ever measured, no doubt. To get even close to starting to get something that looks even sort of like that in the laboratory, we can't just use a black substance. We can't even just use carbonated substances. We have to get this really beautiful layering of this hexagonal planar structure of the lattice. And that's how we get close to making a perfect black body.
I have no idea what we're talking about, guys. I'm sorry. Okay. There's no such thing as we can make an oven out of iron, and then we'll have, when you guys say we can't measure it, we can approximate, what are you talking about? I mean, we can measure it
to get the emissivity as close to 1 as possible.
How do you measure the emissivity?
Emissivity is a really complex measure. It literally has to do with lack of reflection, from what I understand, the way that there's like this NIST database where they test these things out.
Yeah, and what are those predicated on? The atomic structure, the different structure, but it has nothing to do with
structure. It's not the atomic structure.
But you just mentioned like hexagonal. I mean, that's relevant for carbon or something. Iron doesn't have
they use these soot-covered boxes to get the highest.
Yeah,
possible.
we do use that. I should say because we have to have very low reflectivity, high absorption, baffling in our telescope. So we actually have mimicked the interstellar dust clouds that are actually even better than anything we can do on Earth, that have gas clouds. They are not lattices. They are
dust
gas
is
clouds.
Interesting, yeah.
Yeah. So we mimic them. We measure their properties. We found that we have to make the substance one of my friends invented. It's called Bach black. It has carbon. It has glass spheres embedded in it. It has silicate in it. Has a whole bunch of amalgamated stuff. We use it in an epoxy matrix. We suspend that inside of our telescopes to absorb stray reflections, because just like with cameras, you see the reflection in the camera, that's from ghosting. We don't want these photons that have been traveling for 13.8 billion years to be reflected and scattered back to the sky. That doesn't help us at all.
Absolutely.
Right? So we want to absorb them on our detectors. So we're very good at optimizing for these things. So we know how to do these detections. We know how to measure things. Our job is not to measure emissivity. But again, this is like, do you guys want to talk about material science, or do you guys want to talk about the properties of cosmology that render a physical observable into something that we can then use to measure the scale of the cosmos, the age of the cosmos, the composition of the cosmos? Because it really doesn't depend on if carbon, if we didn't use carbon and we use silica, it doesn't have the exact lattice structure.
And it's not as big of a black body.
Okay, but so what? I mean, how do you know
okay,
that?
so the
How do
so
we
what
measure
is here?
that?
The so what is here. So the question that we started with is it possible that there's this piece of evidence that has been measured extraordinarily well? Nobody's arguing about the quality of the measurements of the CMB. The thing that we're asking about is look, there is I know you don't like story. There is an interpretation of that data that is said to be evidence of the Big Bang. Like the CMB is said to be evidence of the Big Bang because of a series of frames of the movie that all sum together to lead us back to the beginning of the universe.
The chain of epistemological
Absolutely.
evidence. Yeah.
Okay. So what we're saying is we're like, hey, Brian, there's a crazy thing that we've come across. We've read Planck. We have been studying black body radiation. We have been thinking about it tremendously. Shiloh and I literally, at 3 a.m., we will wake up and I'll be like, yo, dude, are you awake? And he'll groan and I'll be like, okay, so I've been thinking about lattices. And then we talk for, an hour until finally we can fall asleep. Like, this is something that we spend all of our time thinking about. And we're like, Brian, I think that there's something about material science in the laboratory that is relevant to cosmology that needs to be addressed.
Okay, let me just maybe fast forward to some possibly more interesting things than this. I mean, for me, this is not very interesting, but I will address
But why?
it.
It's the centerpiece of the theory. Like if
The deviations from perfect emissivity for 100% absorption and emission, the deviations of say the what we consider the CMB frame to be about, compared to any other model that purports to explain the CMB's existence, there's 1,000 sigma difference between the postulate that it's dust, that it's caused by starlight scattering or iron filings. Those are completely ruled out, excluded at literally thousands of sigma because of the precision of things like Planck and other things. And let's say I stipulate that the CMB it has a 10% emissivity versus what you might expect it to have. Let's say it should be a perfect absorber and a perfect emitter at all frequencies. Let's say it's 10% off. I think it's the actual number, the Compton Y parameter is 10 to the minus 6. So we can't say it's 0, right? You'll never be able to say with our instruments that it's 0. It's perfect
really
black
good.
body. Right. It's
Yeah.
extremely good, right?
Really
So
good.
let's say I multiply that by, I give you guys 1,000 times more. That doesn't change anything about, say, the Hubble constant, the age of the universe, the composition, when the CMB formed, what the composition was in the CMB. By the way, we don't just get this from like hydrogen alone and the proper. We get it from every single one of the elements that was present then in the early universe. We get it from everything that's interacted with the CMB. There are galaxies between us and the CMB that are at a high redshift. And so they will absorb different wavelengths of light. They have different compounds within them that will cause absorption. And it exactly matches the fact that the CMB at redshift of 1,000 had a temperature of roughly 3,100 Kelvin. And today we measure it to have 2.7 Kelvin, so we get a redshift of 1,100 from that calculation. And if this galaxy is at redshift 1, it will show this exact same scaling by the expansion factor, and the chemicals in that galaxy will exactly absorb as they would at our galaxy at redshift 0.
But that doesn't preclude like.
But I'm saying if I change the emissivity, if I say that we got the emissivity, we made it boo boo, the emissivity is 100 times bigger.
No, we're not saying that. That's not what we're saying. We're literally saying, Brian, what if the source of the CMB is not the story? We're not telling the correct.
You cannot change that. You cannot change the story by that much.
Why?
Using emissivity alone.
Well, no.
Or using any property of the black body.
Hold on. We're using a theoretical principle here. Like we're arguing from. I sound like a dweeb. We're arguing from first principles. We're saying, look, there appears to be a principle of fundamental physics. There's a principle at the heart of physics about black body radiation. It is a very well-studied phenomenon on Earth. And on Earth, the lattice structure, the hexagonal planar lattice, is the only structure that is capable of giving a black body.
I don't agree with that.
That is, if you look up...
It is true, though.
It is true.
So you guys say hexagonal lattice structure.
Yes, so like...
So what is a lattice? I mean, you guys are so flexible with what you're calling a lattice. I can't believe that we're talking about
all
the
of
same
these
thing.
things are made out of lattice, like everything in this room that is condensed matter.
When you say a hexagonal lattice, first of all, there's at least 3 different types of crystal structures, lattice structures that can be present that don't have hexagonal close packing. Is that what you're talking about? hexagonal.
I think graphene's
transpacking.
probably the closest that you're going to get.
Right, so
Like
that's
in the
a
visible-
true hexagonal two-dimensional planar lattice,
That's right. That's right.
But
it's
so
it's a
if I
really
make a
good
black
absorber.
okay, so if I make an oven with a pinhole and a classic black body cavity, and I make it out of iron, completely out of not carbon. There's no carbon in there. Purified it. It's 99.9, 17.9 purity.
Mm-hmm.
You're saying that will be so deviant from what we call a black body that would have some material effect, and it would cause some misestimate.
It'll give you the wrong
of
temperature
macroscopic-
for sure.
Yeah. It will. That's the crazy thing, Brian.
Yeah.
That's the crazy
If
thing.
I said perfect, it's a
It
perfect
won't
iron lattice.
thermalize. It won't thermalize the radiation, so it'll give you the rays will be the wrong color. It's like MRI machines would cook people's heads if all cavities gave the same radiation temperature, right? Like
We're talking about like 80
they're
different things here,
reflective.
guys.
They're
This is-
reflectors, right?
This
So-
is kind of frustrating because this is nothing to do with cosmology. You guys are talking about black body. So let's say you
But
guys
wait,
want to talk about
bodies
black
are at the
bodies.
center of cosmology.
They're
There's
absolutely
Brian, there's a
important to the
cosmological
CMB.
Brian.
Right?
There's a
How do you explain the fact that the temperature predicted that's required for the formation of deuterium, the first non-trivial nucleus, that is predicted to occur at a temperature, which you must know what that temperature is, right? What is the temperature that deuterium fuses at?
I don't know, and I'm
Okay,
not
so you guys
relevant.
don't know that, but you
But
know
it's
everything
not-
about hexagonal lattices
Yeah.
that supposedly have such a big bearing that you get how much you get the temperature of?
That's what I did in my PhD
Okay.
work. That's what I published
I mean,
on.
a lot of
you
people
know,
do
and-
PhDs, but
and
I don't.
I published on
but you're
this
not
in-
you're not studying radiation physics, right? Let me just ask you, how big a difference? Let's say
absolutely.
I heat up an oven, whatever that means. I guess you guys we can't talk about temperature. Like
No,
if I
we
heat it up
can.
if I heat up something to 1,000 degrees Kelvin, and it's an iron, it's made of pure iron. There's nothing else in it. There's no carbon. There's no nanotubes or nothing going on with it, right? I heat it up to 1,000 Kelvin, and then I have a spectrometer. And then I say from the spectroscopic data, what is the temperature that cavity is heated to? It will be off by how much, according to you guys?
It depends
Parts
on.
per
Is it-
billion or factors of 10?
Is it in a cavity or is it able to?
You have a pin. I just described it. It's a classic black body is a cavity that has a tiny little hole.
Mhm.
So that do you know what the cavity hole size has to do with it?
It has to not allow reflections from the room in, basically.
No, it has to ensure that you have incredible numbers of scattering before the light emerges.
It has
So it has
does-
time to do what? To thermalize, right? That's what a black body cavity is. That's what the way Planck constructed this thought experiment. Obviously, you can't build it perfectly because no photons would get out, and the wavelength of the aperture of the black body constrains what modes of light can get out. But you're saying how much would that change the temperature of the black body? As some radiometrist, not a cosmologist, not a lattice expert, not a nobody. What would they measure the temperature to be? I say it's 1,000 Kelvin. What do they say it is?
It will scale by the emissivity. So whatever percentage of one that it is, it will scale. It will be called a gray body as long as it has a Planckian distribution.
Sure, technically it would be a gray body, but how much will you get to misestimate the temperature of it?
It
Depends
depends
on
on the
the emissivity.
lattice. It
Yeah.
depends on. It
I'm
depends
telling
on
you.
the organization.
So for iron, you should know what the emissivity of iron
How
is.
pure is the
It's
iron?
I
different.
just told you it's 17.9. It's pure.
I like.
It should be some
there's
fraction of one.
yeah.
Of course, it's a fraction of one, but that fraction is very important. Is it a part per trillion or is it a factor of 2?
Well, it
Those are
depends. Like, look, let's take a step back from this because you're asking a question that you can look up in a table. Like, we can go and look this up, and there's a database that tells you exactly the emissivity
what
of
the
this
emissivity
stuff.
is, sure.
Okay.
And I agree. Emissivity is never going to be perfectly equal to 1. But that is what matters for cosmology is what temperature do you measure the spectrum to be for these imperfect black bodies, right? That's what you're saying. You're saying
No,
all
that's
cosmology is
not what I'm
predicated on.
saying. That's not what I'm saying. What I'm saying is that perfect thermal spectra are produced by a certain kind of substance.
Specific arrangements of atoms in condensed matter.
Like this is not to say that the CMB is not a cosmic signal. There were, I think that was it Nernst? Oh, Aziz is going to murder me for this. I can't remember who it was, but
Brian's
basically,
saying, there's arguments against, blaming it on background starlight, blaming it on soot.
well, I'm not sure why, because basically, if you look out into
There's
the
ample evidence, but the problem is we can't establish a common language to even have this discussion.
Well, I think
This
that
is
we
what I'm worried
can.
about.
I think that we can, because what I'm trying to say is this. The question that we are wrestling with is whether or not the fundamental principles that inform black body radiation on Earth in the laboratory and the theoretical principles that underpin all of Planck's work if those principles force us to reinterpret the meaning and the interpretation of the cosmic signal that we say is the afterglow of the Big Bang.
But what is the important? So again, I don't know that you guys are really getting to the core issue, which is that the key thing that we get from the CMB is the formation temperature of hydrogen. Are you claiming that because of this emissivity, which may differ at a part per billion, or it may differ by a part per 10 or something like that?
No, all we're saying is that in order to approach such a curve on Earth, you have to use a particular form.
But what does it have to do with like
matter.
but again, what error does that induce in the?
It just might.
Is it philosophical? I mean, is that what you're getting at?
Well, maybe it doesn't
I'm
matter.
really
what we
trying to
call
understand.
Yeah.
Because
like the problem is that if the story that we tell about how to approach this beautiful Planckian spectrum in a laboratory is so wildly different than the story that we tell for how the one in the sky is produced, maybe we should reconsider how the one in the sky is produced, because there's no situation.
But we don't use the one in the sky, which I kind of feel is a little bit of a denigration, but you said it wasn't, so I'm going to take your word for it. But it just sounds like, Sky Daddy is telling us the temperature, right? But I'll take your word for it. You're not denigrating the Big Bang, right? So what we get is one number, which is a temperature, an inferred temperature. We're using the CMB as a thermometer. The thermometer measures one simple fact. It has nothing to do with lattices. It has nothing to do with the interpretations of quantum mechanics.
But what if it does?
Can I finish? Because you guys are interrupting me a little bit more than I'm used to. So
sorry.
I'm used to being on that side, though. So I should be on this side. I know what my guests feel now. But we use that to infer the value of the temperature at which hydrogen forms from protons and electrons, okay? In a plasma, we can make hydrogen form in a plasma. We know what temperature, we know what energy that forms at. We know what the relationship of the binding energy of hydrogen is. We know that to 12 significant figures, okay? These are not like, open for debate right now, right? But we're using the CMB's observation as it was done in 1965. When the value was 3 Kelvin, not 2.7 Kelvin. So if you were around back then, you would say, well, you guys don't even know the exact number to 3 Kelvin. But that didn't change the fact that the universe was incredibly hot and incredibly dense, right?
Well, that's
getting the number wrong.
The story at the time.
But it's not just a story. I mean, it's an empirical
measurement.
observation.
The observation was just the measurements of the temperature of the spectrum, right?
Is a measurement from the spectrum of what the temperature was.
And that's a fact. But then the story you tell about where it comes from is still a story. But it might be an amazing story. Like you might have the best. So
it sounds like you guys want to talk about the philosophical interpretations of blackbody radiation and things like that. I still, if you agree that we can measure the temperature at which hydrogen forms out in any laboratory on Earth, then you can also stipulate that if you can measure at some different temperature, you could say whether hydrogen formed at that time or not, right? So you could say, if the temperature of the universe is above a certain value, it cannot form because it's simply going to be ionized, correct?
I guess I'm not sure that you've measured the temperature of the universe yet. That's all.
Okay, so to say that you don't believe in the state that the observations are credible.
No, they're great observations. The instruments are fantastic, yeah.
So again, it's like interpretations of a black body. Because of a difference which you agree is minuscule at best. In other words, if you have let's say you make I give you guys an oven, you make it out of carbon, you change the lattice, which 100% you guys are wrong about. It has nothing to do with being a hexagonal. You can make a black body out of anything.
You can't make a black body out of a diamond. Like, that's really important.
What do you mean you can't make
a diamond is not a black body?
There's nothing that's a black body.
No, hold on a second.
There's nothing that's a black body.
Hold on.
You guys simultaneously want to say you can get close, but it's not close enough. And even a tiny little thing makes the whole story of the universe being denser in the past completely suspicious.
Hold on. We're not, I think that it's a really emotional thing to talk about the possibility that a story that is so near, a theory that is so near and dear to people's hearts, that is at the center of so much science, might not be the best possible interpretation.
Talking about cosmology.
Hold on. We are, exactly. Because, look, one of your great heroes, it doesn't.
We wanted to just limit it to the CMB part of cosmology.
Okay, yeah.
I mean,
we can do that.
Assuming that's like a third of the theory or something, yeah. The evidence.
The great heroes of your own telling of history are people who stood and looked at something And they were like, they're wrong. Like Galileo is a great example. He was convinced that light had a speed. And everybody was like, no, it doesn't. And he came up with experiments. You know the lantern operator experiment?
Well, that was Gauss, but yes, Galileo's.
He proposed it for the first time. So Galileo was like, take 2 lantern operators and train them to open and close the flues of their lanterns when the light signal arrives, get them to be able to do it really fast, and then move them farther and farther apart from each other. And eventually there's going to be a little bit of a delay between one opening his flue and the other one closing his upon the arrival of the light. The Institute of Science in Florence tried it in 1716, my dates are horrible. They tried it at the distance of a mile with a telescope, and they were like, there's no difference. There's no tangible speed of light. It must be instantaneous. Okay. And so we know that history is littered with people who stood at the edge of a consensus perspective on what the data says about the nature of reality. And at some point, they were gripped by the horrific realization that something had gone wrong in the story that everybody was telling.
Yeah, but as science progresses, and as I mean, you could say the exact same thing to cast doubt on evolutionary biology. Would you do that?
I think that evolution
it's a much
is
weaker
missing,
story.
I think
right?
evolution is missing key parts. I think that there are huge
Every
gaps.
scientific theory is missing some observational data that's
Absolutely.
inaccessible and permanently so, right?
We should have we should get together over coffee and we can tell you about all of the things that we think are fundamentally missing and improperly interpreted in Darwinian evolution. Like, we can do that for you. Okay. What we do is we go out and we look at theories and we try to find the pieces where everybody is like, this is what this means. And we're like, there are different ways of seeing it. And that's what we're trying to do for the CMB.
That's fine, but you guys are making fundamental factual errors.
We're not. We're not,
okay,
because
and
the reason
smacks of such insubstantial epistemic, humility that you guys are not. You guys are more expert than all the scientists that come before.
No, we're not.
I'm not even talking about me. I'm not even going to be. I'm not offended that you guys are questioning this thing. But I'm saying you've made fundamental category errors. You've said things like lattices are important to black bodies. They're absolutely not.
Okay, I can demonstrate this too.
I don't think that. Okay.
Brian, let me demonstrate it.
Okay, go on.
Okay.
What would you like to say?
Graphite is a pretty...
I want you to just answer one question. Can you have a black body that's in a gas?
No.
Never.
No.
You can't have a black body that's
never been done before.
I don't think that... What do you mean it's never been done before?
No one's ever done this before.
What do you mean no one's ever done it? Does that mean it's fundamentally impossible? I mean, you guys are mixing up very simple things, right? You're saying that because a human being makes an error and our apparatus is flawed in some sense, that it's the concept doesn't exist, that there's no way to get it.
I think there's a material basis for why it's the case. Like, I think physics all has a material basis to it. I think
there's no such thing as a perfect black body.
There's a reason why black bodies give that spectrum and gases don't, though. Like, the gases have a different limited set of vibrational freedom compared to lattice-bound atoms.
So you're saying a lattice can be a perfect black body?
Only lattices can be perfect.
Okay, that's... And you're saying on Earth, like a human, grown crystal, you can actually make not an approximate black body, but you can make a perfect crystal. I mean, you can make a perfect black body from some man-made object.
Not as perfect as a CMB.
Hold on. Okay. Hold on. This is important. So, not as perfect as the CMB, for sure. You're totally right. The quality of a black body depends intensely upon its lattice structure. So, like, what a black body is anything that can take a certain continuous spread of wavelengths, absorb them completely. This is like perfect black body.
Any wavelengths. Or it doesn't have to be a
So if I took carbon, in the interest of time, if you took carbon and you atomized it, you made it into a gas, could it be a black?
No, not in a million years.
So only in a solid can you have a perfect black body. Can you have a perfect?
It's not perfect.
In a carbon and a diamond. Of all those, look at those 119 elements over there. Diamond so only one out of all of those is... So shouldn't we call it a carbon body? I mean, you guys are basically making an assertion, which I've never heard in my entire history of studying radiation physics.
I know.
But you guys don't have domain expertise, in terms of like what a scientist would say about something. You're making up a statement that is provably false because you guys have confused things like gas. Like, you're saying that a gas cannot be a black body.
Yes.
It is true.
No matter what density it has.
It is
true. So plasma could... So the whole notion of the temperature...
At least it has never been done.
Well, again, that's irrelevant.
But how do you
We're
know
talking-
how do you know it can if
I'm
it's
talking
never
about
been done?
we're talking about a model, right? So a model is going to have some approximations. Just because we haven't done it doesn't mean someone won't do it tomorrow.
But we want a really good model, don't we?
Again, that's such hubris, right? You're saying because we haven't done it, because I haven't done it, that it will never be done.
No
and
one's done it.
I would like to make my case about lattices. Let me make my case about lattices. Look, if you take a substance like carbon and you put it into one kind of lattice, you get a diamond, which is not a black body. It is not a black body. It cannot thermalize radiation. It cannot.
Of course it can.
No,
it
it
can come
can
to a temperature.
Hold on.
Transmit
This
it.
is important.
You're just wrong. It can come to a temperature. It can be measured using a variety of different
Hold on a second.
thermodynamic
Black
techniques.
body radiation is a thing that tells you about the ability of the object to absorb certain wavelengths of light, transform those wavelengths of light into heat, and re-emit the heat thermal motion of the lattice as a new kind of thermalized light that accurately predicts the relationship between the shape of that curve of light and the temperature of the underlying body. That is what it requires for something to be called a black body. Diamonds do not do that for visible light, but carbon, black, and like Vanta black and all of these crazy space age MIT paints, which are vertically arranged carbon nanotubes, can do it. They're
So
like
they can make perfect black bodies.
they're
Okay,
like 99.999%.
Anywhere right now. So I want to make a suggestion. We agree to disagree about this. I fundamentally disagree that you can only make black bodies from carbon, or that they've only been made on Earth from carbon. Again,
We're talking.
I want to talk about the difference that's critical for cosmologists like me is if you stipulate that the black body spectrum of Planck, Planck radiation spectrum, which comes from the Bose-Einstein spectrum, if you say it has some deviations from being perfect, it's a gray body, you can say whatever it is. As soon as you tell me what bounds you say are acceptable, then I can start answering questions about how it pertains to cosmology. If you want to say have a long theoretical discussion about black bodies and are there such things as perfect black bodies, I mean, you mentioned things like the speed of light. Like, how do you measure the speed of light? How do you measure it?
Ole Romer measured it by putting together ephemeres.
That's 200 years ago. How do we measure it now?
Presume some kind of laser and mirror array with interferometers.
No, it's a defined quantity. It's not measurable. We have accepted that it's a stipulated constant. There's no uncertainty on it. It's a defined measurement. That means we measure everything else in terms of it. So it's not something that you can even speculate upon if you're going to use the system of units that we use to measure. You can make your own, where light's meter's constant, and then you have to define that in terms of something else. Speed of light's a defined concept. So right now, I'm nervous because, again, these are basic concepts for physicists. It sounds like you've talked to people that have gotten you all bothered about and interested in. I know.
Like, he's the father of physics.
Okay, so it's 100. Well, he's not the father. I mean,
a lot of people of quantum. Like
Lord Kelvin basically came up with the idea of the black body and the measurement at the Kelvin scale, right? And he also thought that there was essentially physics was complete in 1899.
Sure.
2 years before. So this like hero worship of Planck, I think, is really misgiven. I mean, I think he was certainly a great scientist. I mean, he was an incredible intellect. But to say that like he's the final word or somehow
no, he made
philosophical,
some mistakes too, for sure.
Of course he did. He's a human being, right? All human beings make mistakes.
Well, he made a really interesting one in that paper. I've been reading it lately. His treatise on
I haven't
heat
read
radiation.
it, so you probably
I mean, it's a bit of a nightmare, but it's really difficult and intense. But
so did Maxwell. Maxwell had a theory. You must know this too, right? He had a theory about the speed of light coming from the electromagnetic, the ratios of the permittivity, the permeability of free space, what he called free space. And he came up with a number that's, it's accurate. It's not close. Do you know what his underlying theoretical concept was?
Yeah, he was like, they're the same.
No. He said that there's an ether. He said there's an ether made of vortices, gears, and whirlpools, and those sustain the magnetic induction. And he didn't come up with the 4 laws of Maxwell's electromagnetism. Oliver Heaviside did. And he had to convert it into a pair. And then we go out and measure it. Again, now we define the speed of light. So again, I'm not sure. I thought we were having a conversation about cosmology, right? So I thought we were going to talk about cosmology. And again, you're kind of like squirrely avoiding this question. I want to stipulate. Let's say I'm totally wrong. Big cosmology. Eric Lerner's right. Convince me. I'm totally. I'm not. Just let me finish.
We're definitely not flying that
let me. Well, you mentioned alternatives. You mentioned like all these things hinge on this one thing.
The world of people that are saying that there are different ways of looking at this is so big you cannot imagine it.
No, I imagine it. I also imagine the
And
world
they
of
are
credible people
they are credible and they are reputable. And
give me some names though of people that don't believe that the CMB is representative of a black body state originating from an early hot dense state.
I don't
Name
know.
some people that,
Well, I
that
don't know,
don't
but
believe
I don't
this.
want to make this about belief, though, right?
No, but you just said there's a world of people that's so big I can't believe it. I can't believe it. You're right. So tell me some names of people that are credible, published, scientifically vetted, have laboratories, have done experiments, have attempted to make these measurements, or is it people speculating because they have tokamak reactors, they have their own things they want to do in Pennsylvania or wherever? Tell me the names of these people, these credible people that you guys are mentioning. That's this world of people, Anastasia. You should be able to tell.
Well, I don't necessarily think this is about appealing to anybody's particular authority. It's really about trying to understand something.
I'm just mentioning. She mentioned.
Yeah, I know, but I don't think that's what you wanted to get into.
No, I think that I don't think that the point is to name names. I think that there is a really serious tendency to denigrate anybody who comes around to say, "Hey."
No, you're wrong. Scientists are
But
the
Brian,
most denigrating it. They're the ones that will denigrate their opponents, scientifically speaking, not just based on their personality. I'm not making ad hominem attacks. I am asking, do these people have credibility? I get 100 emails a day from people that have solved these problems and the theory of everything has been unified. Quantum gravity exists. Right? So you get all these emails, right? There has to be some gatekeeping, right? I'm sorry. If you say that there's gatekeeping is bad, I fundamentally, thoroughly disagree with that. Just as I have a gate around my pool at my house, we have a gate around our country. We have gates that serve certain purposes. We have gates on this campus to keep certain people in, certain people out, right? So
who are we keeping in on campus?
Who are we keeping in? Hopefully the professors. No, hopefully the professors doing some work. But philosophically, you guys will not tell me the degree to which this matters. I will stipulate the CMB is not perfect. I will stipulate that diamond is not a perfect black body.
It's actually really
not a black body.
It's not even black.
Fine. And I will stipulate whatever.
Gray.
So you'll find these different things. You can measure their spectrum. You still haven't told me to the degree that we assume in our model, which you call a story, whatever, in our model of hydrogen, the simplest element on the periodic table, the most well understood atom that exists, the foundation of all of modern physics and thermodynamics and all sorts of other things, astrophysics. You still haven't told me how big of a difference are we talking about here? Because let's say we had the universe was made of carbon, so it was a perfect black body, or it had the potential to be a perfect black body. Again, I don't agree with that, but let's just say it was made of carbon. How much of a difference would we underestimate or overestimate the age of the universe, the big pillar, or the fact that the universe is expanding? Would we say the universe is contracting? Would we say the universe is 1 trillion years versus 13.8 billion years? Well, tell me, give me the brass tacks here. Tell me exactly what are we getting wrong and by how much? Tell me the quantity of it.
Can I take this one maybe? I mean, I can see the confusion. So we're not saying that the CMB is an imperfect black body. We're actually suspicious of how perfect it is. We think, wow, that's a really interesting phenomenon that you measure something that should come from condensed matter here on Earth. And what's really interesting is that the CMB was first discovered on Earth. Then it was really tightened up in terms of error bars by these weather balloons, and then it was measured. It
wasn't first discovered. Again, you guys are these are simple things.
It
was discovered in cyanogen molecules in 1947 in our galaxy.
Well, there was a guy who proposed that the cyanogen temperature was perhaps a source of the universe's temperature that was related to the Big Bang.
He measured it as a detector. He used cyanogen in the Milky Way galaxy and its absorption features, which, as I mentioned before, was been used in other galaxies, not even just in the Milky Way. And so when you say something's measured on Earth, again,
but he wasn't when he published the cyanogen measurements, nobody accepted them as being evidence of the Big Bang. The provenance of the CMB as being, what's that?
It was in the data. I mean,
it wasn't a black body either. It was just a Rayleigh-Jeans approximation at best. Like they're just
it's a molecular absorption feature.
Everybody was predicting temperatures. People were making all of these crazy predictions.
The dominant paradigm was the universe had no temperature, or it was a concept from starlight. That was its dominant temperature.
The steady state people were arguing that, at first for sure. But my point is that so they measure this incredible thing right here on Earth.
But they didn't do it on.
Well, they do. They measure the black body.
What do you mean
on
Earth? What do you mean the black body on Earth?
Well, there was a horn antenna that Penzias and Wilson used in Holmdel, New Jersey, to get a signal that was measured first terrestrially.
at several frequencies. At first, it was
But what does it
also a
matter?
relation.
What if he built it on the moon? What does it matter that he made it on Earth? Or
Well,
that
that's
Penzias
what's
and Wilson
interesting.
built it on Earth? And by the way, I knew
we have a lot
both
of condensed matter here on Earth, right? So like they go up, right? They go in these weather balloons. They're still getting it. It's a perfect black body. They go up to.
It's not a perfect.
They do the
nobody
COBE
ever
satellite,
has said
right?
it's perfect. Nobody's ever said it's
We agreed at the beginning of this conversation it was very near perfect.
I said it.
It's the near.
But there's a huge difference. There's an infinite difference between nearly perfect and perfect. If I say the Earth is a sphere, am I saying it's a perfect
it's really
sphere?
good.
It's not a perfect sphere.
I'll go with really good. It's really, really nice.
It's the best one that we know.
They measured at COBE. It's really, really nice.
Until that was in the year 1992, right? Yeah.
But that's where all of the direct measurements of the CMB come from.
That's outer space, right? But you said
it's very low Earth orbit, right?
No, it's not in low Earth orbit.
COBE, absolutely.
COBE was in Earth orbit, but it's not on the Earth. There's no atmosphere. The atmosphere.
It's very near a bunch of condensed matter is what's interesting.
So the condensed matter of the Earth affects what properties of the radiometer that FIRAS used, the far infrared absolute spectrometer.
It's the closest source of anything that approximates what would give a black body Planckian spectrum in a laboratory is the Earth.
What is the Earth? The Earth itself is I thought carbon's a black body, nothing else.
The Earth, here's the thing. You can have a black body, a Planckian spectrum that gives you the wrong temperature. Then we call it a gray body, right?
Yeah, you would impute
because
the
it's got imperfect emissivity. Perhaps the Earth is a gray body in some sense. I mean, the Earth is like 70% water, the surface of
Wouldn't
it.
Wouldn't that then decrease the validity of your argument because you're contaminating a black body with a gray body?
It would give the wrong temperature.
So, but we don't see any evidence of the CMB being afflicted by gray body attributes. So how do you reconcile that? If the Earth is this big contamination source.
Gray bodies have a shape that looks just like black bodies, but they give you the wrong temperature.
The amount of, do you know what the atmospheric density is at the height of COBE's orbit at 250 nautical miles in the polar orbit above the Earth? Do you know what the...
Probably not much.
It's effectively zero within our measurement. So it's not an atmospheric effect. No. It was shielded by over 100 decibels. This is something
it would need a lattice. Yeah, it would need a lattice.
So where would there be some lattice floating around?
Yeah, so I mean... Like this kind of goes, you know, I'm not saying I know the source of it. One possible reasonable candidate, if you're looking for if you're looking for a hexagonal lattice, there's an enormous set of hexagonal lattices in the surface of 70%.
So other atoms, any atom that if I made iron into a hexagonal lattice, whatever that means. By the way, hexagonal planar versus hex cubic close packing. I don't know what the difference is.
We have reason to believe, like this is perhaps where my own research is relevant, that water does form hexagonal planar lattices, actually, especially under pressure in bodies.
I'm sure it could.
At surfaces.
I don't dispute that.
So that's kind of interesting that there is a
How does that affect the age of the universe?
Well, the question is whether or not what you're claiming is a cosmic source is in fact cosmic. Because if it's actually coming from the Earth, then it's no longer...
But you just said the effect of the gray bodiness caused by I could put a whole spacecraft made of carbon nanotubes or whatever Anastasia was mentioning before. I put those in low Earth orbit or whatever, measure things from the Planck satellite, which also measures this, and the inverse Compton scattering.
Is the Planck the one at L2?
Yeah, Planck and WMAP, both WMAP and Planck.
They didn't measure the monopole at L2 or the dipole. They just had used calibrations from COBE theory. So they didn't measure the CMB there.
They measured the annual modulation of it. They measured the modulation of the dipole.
They didn't actually record the CMB.
But they were measuring something that wasn't the CMB.
They were assuming the temperature of the CMB and measuring a differential radiometer that looked in two sides of the sky and compared.
Yeah, but as you must certainly know, you get when you expand the multipole expansion of the CMB, you get a term that depends on the absolute temperature.
That's just an expansion, though. They didn't directly measure the monopole or the dipole. They calibrated.
But all those are connected to the. No, they actually calibrated from the different. Again, you guys are making very simple mistakes.
No, it's not.
They don't calibrate from the monopole. They don't calibrate at all.
They calibrate from the dipole and
they calibrate from not only the dipole. There's multiple dipoles, right? What is a dipole caused by?
The proper motion of the Earth with respect.
No, not the Earth. The spacecraft is what is measured.
Well, it's rolling around with the space.
No, the spacecraft has multiple. No, it also is attached to the galaxy, Shiloh. So there's many different dipoles that they can measure. This gives you multiple avenues of attack. Just like looking at the paleontological record gives you information. Looking at the geological record, they give you multiple things that all point in the same direction.
Isn't that crazy? They didn't directly measure the CMB at L2. Like, why not? That would have been so easy to do.
Do you know how hard it is to measure this?
No, they could have used the same kind of horn that Furious was using.
Absolutely. So you guys, this is now slightly, So the deviation from the black body that they measured in terms of Compton Y, gray body, emissivity, and the deviations that will also be present in the Sanyaev-Zeldovich effect and the inverse Compton scattering that occurs, which I'm assuming you guys know, but I'm not 100% sure because you're not experts in the CMB. But those effects, they all come out with the same exact temperature, and the deviations are at the part in 1 million from Compton Y. So now you're going to tell me that that effect, whatever that is, and no one scientist is saying it's a perfect black body. They'll say it has this chemical potential limit and it has this Compton Y distortion. There's another type of distortion you can get in very strange cases where there's energy injection that occurs later. We've limited all those are parts per million. That has no bearing on the age of the universe or any other statement of the fact that the universe was smaller in the past. Then I add, hold on, let me finish. Then you add on to the fact that we measured cyanogen in our own galaxy, measure other galaxies have cyanogen, you measure other molecules and the spectral and vibrational characteristics of a book that's right there that has, by Charlie Towns, that has the rotational and vibrational spectrum of literally 1,000 molecules in the microwave spectrum. They all come out with the same value for the temperature. How is that? How is that orchestrated? By what mechanism did a galaxy at a distance, let's call it a distance, not even call it a redshift, some distance of a million light years away, or even more, because that's close. How do they all have the same temperature?
Okay, so can I take this one? Yeah. Like, if there is a background temperature of the universe, is not the question. The question is the background temperature of the universe coming from a gaseous substance 13.8 billion years ago prior to the existence of atoms? Or is it some kind of signal being produced by the thermal equilibrium of objects with lattices spread through the universe today?
That didn't exist. Where did carbon
What do
come
you mean
from?
it doesn't exist?
Carbon didn't exist.
Like, that's the whole point of the argument, Brian. I'm literally saying, if you cannot have black body light come from something that does not have a lattice,
nobody has ever published, as far as I know, in the cosmological
Brian,
context.
I hope that you do not think that the quality of an idea is dependent upon it being published in a scientific journal.
This is a ridiculous argument. If I say to you, I've studied the Kennedy assassination last night, but I don't have a PhD in chemistry. I don't have a PhD in ballistics. I don't have a PhD in the meteorology in Dallas in 1963. Is that all the same thing?
Like, Brian,
do you take all people's credit? Like, anybody has an idea, we're supposed to weight those equally in some
Brian,
Bayesian
I'm
framework?
literally sitting in front of you, and I'm like, look, the fundamental theory that is at the basis of black body radiation demands that there is a hexagonal planar lattice.
I would like to see the data on this.
Okay,
I would like to see the data. I would see a publication. It should be abundant. I mean, it should be like, we should be teaching that there's a flaw in Planck. Let's stop talking about cosmology, because we haven't really been talking about cosmology, let's be honest, right? We're talking about something to do with black bodies, which may have some, we haven't gotten to real cosmology.
Well, this is essential theory. This is a piece of evidence at the heart of cosmology.
I would like to see something, and if you say that peer review is bogus and
no, that's not what we're saying. That's not what I'm saying.
So you will be able to provide me with peer-reviewed articles, not necessarily by Sheila.
No, Brian, we want to write that peer review article with you. You don't understand. Like, we're literally sitting here and we're like, Brian, you are brilliant. You are at the top of the world. You should look at this, because this is the future of these ideas. And you are the guy who's going to write this, and you are going to revolutionize science, because no one has paid attention to this. Like, there's some people that we know, and I'm like, Brian, somehow everyone has missed this, and it is crazy.
Do you know you sound crazy?
I know.
Yeah, okay.
I know.
Fine.
But I'm telling you, it sounds insane, but it is
Copernicus sounded crazy too, you know?
And I'm literally
I get those
He
emails
didn't get a Nobel Prize either, by the way.
Yeah, exactly. But, you know.
But I'm like, but Brian.
Tesla was crazy, and Boltzmann was crazy, and he killed himself, right?
Right.
Okay.
And now it is our turn to do
right.
statistical mechanics. I'm like, look, I know that it sounds like a philosophical distinction, where I'm like, hey, the black body thing here is important, and the lattices are important, and the structures are important. And that's why we're here, because we're like, Brian, no one is looking at this. We have been reading Planck. We have been looking at fundamental physics. We have been studying the nature
I don't
of
think
light.
you should read Planck. I think you should read modern statistical mechanics, modern plasma physics studies. I think you should visit tokamaks. I think you should visit other.
They don't make black body radiation.
They pull their
I know
universe.
you guys are saying that, but you have to be 100% bulletproof confident
Would you take-
that it's completely impossible.
I wouldn't have come here if it was possible.
Well,
I
I
wouldn't have said such.
Well,
such
guys,
Can
you're
we ask
you're
AI?
confusing
Can we
something.
ask AI?
No, because AI will tell you whatever you like. AI told me, ChatGPT told me that I wrote A Brief History of Time. It literally said,
Amazing.
it was one of the books. I said, thank you, ChatGPT. Can I have 1% of his book sales, please? No, that's one of the big red flags, by the way, to your audience, because I do offer. So what I've done is when people want to have their idea and have me share either in a Nobel Prize or something, or in the discovery of all time, really, it sounds like what you're claiming potentially could be a discovery of all time, right?
I don't think so.
Well, it's a monumental. I mean, you're talking about Copernicus. You're talking about a lot of big name people, and I'm saying if this is true and it's revolutionary, yes. So you would want me to be a part of it. I'm honored to think about that. I get 10 of those a day, right? So one of the first things I do is someone sends me an email. I literally did this before this interview. I have an autoresponder on my phone. Someone writes me this. They have this paper they want me to read. I say, thank you very much for your email. I'm very overwhelmed with my own research, education, family topics, travel, and all writing and doing all sorts of other. Plus, I have a podcast, by the way. I don't know if you knew that. But I'm willing to evaluate your theory or your idea. I charge $1,000 per hour, donated to a food bank on campus at UCSD. I don't get any of the money. It's donated to the Triton Food Pantry. I'm a huge supporter of it because tragically, some of the students here are food insecure. First hour is $1,000. Next hour is $2,000, $4,000. Keeps going up like that. Take as much time as you want, as long as it works with my schedule. And uniformly, I've gotten many people to do this. Many people have submitted, put their money where their mouth is. Not just come here guys put a lot of effort into coming here. I'm really appreciative of it. But put thousands and thousands of dollars towards the Triton Food Bank. So the students here should be grateful to these generative ideas, right? Not a one of them did not have their reviews, their thoughts or ideas reviewed by AI, okay? Multiple AIs. And what's interesting is all of them were substantiated by the AI, and more than that, the ones that are in conflict with each other, because I get them all together at certain points.
We see this.
They're also consistent with ChatGPT or with any AI or Gemini and multiple AIs, right?
It is crazy.
It tells us nothing about it. So
Well, it does
that is not. We could say a fact. Like you could ask.
I would just ask
does
it.
plasma?
Just treat it like Google. That's
Yeah,
all.
like
Well, but it also hallucinates. So Google, theoretically won't hallucinate. If we look up, but that's why I want to restrict the domain of what we're talking about to peer-reviewed. And you're going to say, well, it has nobody to peer review it. Well, that could be a sign that you're not barking up the right tree. You have to admit that, right? I could be wrong. You guys could be wrong.
It's a first principle argument more than an appeal to any particular body of literature other than the classics that we're all aware of. I think actually, like for us, the best case scenario is just that you see what we're saying, not really that you can say it's stupid or useless or has nothing
sometimes
to
just
do with
offering to have me involved in it and stuff like that. But I'm not an expert in black body. So again, I judge my students. I judge my PhD. I judge the people that submit their theories to me by the quality of at least the legwork that they've put into it. Now you talked about your research into lattices and whatnot. Great. So you've done something, you've done domain. But if you did your homework, you would know I'm not an expert in lattices and carbon and stuff like that, nor would I claim to be. I am an expert in experimental cosmology, radiometric physics, atmospheric phenomena, absorption.
No, dude, you're a
all sorts of
complete badass.
No,
Like that's why we're here. Is we're like, yo, dude, there's something really crazy we noticed, and like I think it's important.
But why not go to an expert? Go to a plasma physicist. Why not go first to a plasma physicist, someone to talk about all these different things, and then go to other people? Like, I mean, you just said something that's.
What do you think our podcast is? Like, that's what we do.
No,
we do
but
it
I mean, you
twice a
talk
week.
to people that are not necessarily domain. If you talk to Terrence Howard about the CMB, that would be a big mistake, right?
No, we talked to Terrence Howard about his theory.
You talked to him about his theory, right? So I'm not a black body historian, right? So I'm confused why you're talking only about that. Like if I was on
terrible because I feel like I'm upsetting you, and I just thought that we'd tell you something.
No,
I thought we might just point something cool that maybe you would roll around in your head, and maybe you would make
I would have liked to talk about that for 20 minutes. Yeah, I feel like we spent the whole time, which is coming to an end, not discussing my research, not discussing new findings, not discussing the exciting developments in this field, but slightly coming to it from a perspective that we may have all gotten it wrong because of this one weird trick that, Planck
Well, we
noticed.
have a chance to get it right, man.
But again, so I would say that's great. But like, if you guys have some idea that, cancer is caused, in the bloodstream by your carbon, nanotubes in the environment, microplastics or whatever, and you're talking to me, I'd be like, these guys don't know what they're talking about, because they're not talking to an expert in that field or someone that can give them any credence to it other than defend my priors, which is that the universe has abundant evidence, which I haven't even had a chance to get into. That does frustrate me, for abundant sources of evidence that the universe has this. And every time we pivot to it, you guys are kind of like, well, this is only true, for things. And we really, the Planck satellite and WMAP should have built this other thing that would have made it possible. I mean, once you measure the parameter, there's absolutely not, we don't go out and measure 21 centimeter radiation from all these different locations because it could have been caused by some other effect, and build every instrument has to be a 21 centimeter radiometer, right? That's impractical. And once you measure something in science, the burden is on someone who's challenging it to provide substantiation that it's not constant, right?
We actually might have a millionaire who is going to help us build a satellite to go measure them. And it'd be really interesting, because I don't think it will tell us whether it's a cosmic source or a local source, which would be really cool, because it will contribute to us not having to ask such a stupid question as to whether the CMB is there at L2. Right? So that'd be really cool.
So if we had more time, I would say, because I told you I have to leave it.
We'll come back next year.
Yeah. You're more than welcome to come back. and next year, you should have, by all rights, a lot more evidence, and maybe we'll have just like some. I mean, you cannot tell a credentialed scientist that his or her credentials don't mean as much as someone who has an interesting idea, who's read a lot of papers, who's incredibly invested in this topic for reasons that may be of interest to them, may be of interest to the whole world, in correcting some big mistake, right? You can't go to an oncologist. Again, go to an oncologist and tell them everything they know is wrong. And we have an idea that they're wrong. We can prove it. We do need their help to do it. And then the work that you're trying to do is in plasma physics. I mean, it's going to be something that's gonna not sit right with the expert, right? Expert is somebody who's very, hold on a sec. An expert is someone who's excluded so much potential knowledge that he is or she has made a complete career out of one very narrow aspect of their lives, right? So because I'm a cosmologist, it doesn't mean I'm a black body expert or anything. But within the domain of cosmology, we can talk about black bodies. We can talk about what's been measured, right?
I hear you.
Yeah.
And
so I think this is all,
hold on. I think that you're letting him off too easy. I know. I'm sorry.
He's never going to let us continue this conversation.
Well, I do have to go babysit some kids.
Study the CMB.
Yeah.
Like, it's not an irrelevant question to you to be like, hey, hold on. Can we talk about the first principles of physics that go into the signal?
I would, but I'm just not convinced that, to be honest, as friends, I do enjoy talking to you guys. I think you guys do something very valuable. You've made a couple of factual errors.
Let me write. Can I write those down?
The fact that lattices are the only possibility of a black body is in a specific carbon lattice.
I didn't say that. I said a planar hydrogen lattice.
A planar hydrogen lattice now?
No, sorry. Hexagonal. I had the H.
Okay, so hexagonal. Okay, so fine. But then when I ask you, like, can you show me some peer-reviewed referee data, publications, eminent scientists?
This is probably the best source, right? Because they're going to tell you what the best black bodies, and you can see that they come from these, first of all from lattice-bound.
And you've also said that gases cannot be black bodies. There's no black body whatsoever, but you've also said it could be a gray body. So it's not really clear.
Gases wouldn't give you gray bodies either.
There's no and plasmas can't produce. You said that the plasmas aren't produced in tokamaks. You've said there's no characteristic
plasmas
temperature.
Are produced in tokamak.
Right, but the plasma doesn't has any temperature.
Yeah.
So the temperatures that they speak about when they create a plasma, what are those temperatures of?
The intensity has some non-Planckian frequency distribution.
The temperature is only discussed in the context of molecular or ionic physics. in the average kinetic energy of a typical particle, of a typical molecule or ion.
So you won't get that nice fingerprint line spectra that you do from the black body from these.
Well, there's no fingerprint. I mean, black body is defined by a complete absence of spectral features.
Well, no, it's this nice, beautiful line shape, right? It has like.
You mean the Planck shape of the curve? Yeah.
Intensity versus
but there's no
temperature.
fingerprint. I mean,
that's what the fingerprint is.
That's
the Planck
chemical
shape.
fingerprints we typically talk about as emission absorption spectrum of atoms.
Well, this is the emission absorption spectrum.
And that's how we measure, by the way.
Atoms,
right. So when we measure the sun and we measure its temperature, we are measuring what? What is it producing? Where does that temperature come from?
That's also a very, well,
it's not a, you agree it's not a hexagonal lattice, right? The sun is not a hexagonal lattice.
Let's talk about that next time.
Okay. All right. Well, this has been fun. I'm going to go out and suntan later on in a non-black body. But thank you guys for coming out. Enjoy show your friends the Keating medal, because that is what I want to present to you here. I will show it to you guys.
All right.
So the Keating medal for impossible imagination, featuring Sir Arthur C. Clarke on the front and featuring Demystify Science with today's date, December 18th.
You
see this? This is not just some generic thing here, guys. And this is a monolith from 2001: A Space Odyssey. So thank you guys so much for coming. Enjoy your Keating medal for impossible imagination.
Thanks for putting up with us, man. I appreciate it.
It's fun. Happy New Year, healthy New Year, and let's do it again exactly at this time.
We'll be here.